At the end of our last video, we were just beginning to discuss how to convert through a multi-step molar conversion. You would know that you had a multi-step problem because the question is going to be missing the word moles. Every practice problem so far has said how many moles or has provided you with so-and-so number of moles. In these problems, they'll be similar to the ones below that say how many grams are in so many molecules, or how many liters are found in so many grams. And we began to discuss the general equation. We said when we solve these, it's going to be the given over 1 mole over x, and then y over 1 mole, where x and y are either the molar mass, the 22.4 liters, or the 6.02 times 10 to the 23rd. Here, this is really where that map comes into play, so we're going to go back to that briefly. So now, basically, you could be asked to start with volume and go to mass, or start with particles and go to mass, or start with mass and go to volume, or particles and volume. So you can convert between any of them. The mole is the central unit. So we're going to use the mole map to assist us with this. If we wanted to go from volume to grams, we would follow this path. So we're going to first go from volume to moles, using this as our conversion factor, and then continuing to follow the arrows to get to mass. We would use this as our second conversion factor. You'll notice that the first one is 1 mole over a number, and the second one is a number over 1 mole. We're going to go through a couple of practice problems here. It's still dimensional analysis. We're still going to be crossing out our units and things. It's not too bad. Here we go. So, first one says, how many grams of NH3 are in 5.66 times 10 to the 24th molecules? So since the problem says the word grams, I know that I'm going to need my molar mass. So I'm going to solve that now. Nitrogen is 14, and then hydrogen is 1 times 3, so I get a total of 17. So now I'm ready to solve my problem. I'm going to start with my given, my 5.66 times 10 to the 24th molecules over 1. And I'm going to use my general equation. I know that it's going to be a division-based problem where 1 mole is on top. Molecules needs to diagonally drop. So my bottom is going to be 6.02 times 10 to the 23rd. And then the problem is asking for grams. So currently I'm at moles. I need to diagonally drop the moles. So 1 mole goes on the bottom, and the molar mass of 17 grams will go on top. And then I will mathematically solve. I'll divide and I'll multiply. And you should get right around 160 grams. So 160 point for the sig figs grams for your answer. Okay. We can cross out units that are top and bottom. So molecules and molecules, moles and moles. And you'll notice you're just left with grams, which is what we want. Okay. You can use the map to assist you with these for now, if need be, but the general equation always holds true. At this time, please pause the video and try the provided practice problem. Please check your work. The molar mass of water is 18. So I put my given grams over 1. I diagonally dropped grams, so they'll cancel. And then the problem's asking me for liters. So I put my liters on top. My grams cancels. My moles cancel. And I'm left just with liters. And I would go ahead and multiply and divide this out. I rounded for 3 sig figs because my given was 3 sig figs. Okay. Let's kind of switch gears now. We're going to start our study of chemical reactions. We're going to start by beginning with some of the basic information about a chemical reaction. A chemical reaction is a chemical change. They're interchangeable. When substances combine or rearrange into something new. They are composed of two parts, your reactants and your products. The reactants are on the left side of the arrow. The products are on the right side of the arrow. So these are often referred to as the ingredients of a reaction, and the products are the results of the reaction. Reactions travel reactants to products, and atoms are not created nor destroyed because of the law of conservation of matter. There are some symbols that are used within a chemical reaction. An arrow, which stands for to yield, to form, or to produce. A plus sign stands for and. For example, hydrogen and oxygen react to form water. Or sometimes it'll just mean reacts with. We have a variety of states of matter, most of which you should be well aware of. S, of course, stands for solid. L stands for liquid. G stands for gas. And AQ stands for aqueous, which means dissolved in water. Most solutions that we deal with are aqueous solutions. Reactions can also sometimes have a triangle as part of the reaction, and this triangle stands for heat, either being released or absorbed. We'll talk more about that in a later chapter. Let's continue our basic knowledge on chemical reactions. There's a variety of different ways to write out a chemical reaction. You can see it written out in a sentence, as it is here. Copper reacts with chlorine to form copper 2 chloride. It could also be written as a word equation, copper plus chlorine, arrow, copper 2 chloride, or as a chemical equation, Cu plus Cl2, arrow, CuCl2. This is the form that we are primarily going to be working with. Okay. You may have noticed that here on this side it just says the word chlorine, but then here in the actual equation, Cl had a 2. That 2 is not automatically just because this is a 2 over here, but because certain elements on the periodic table are diatomic. Di meaning 2, atomic meaning atom, so 2 atoms. We have some nonmetals on that table that cannot exist alone. They are known as the diatomic. The 7 diatomic elements are nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and then hydrogen. So what this means is that on the periodic table, if it's an element by itself, so if it just says nitrogen, it's N2. If it just says oxygen, it's O2. In the example, it said chlorine, which meant Cl2. Only when these elements are alone do they get a 2, because they're unstable without a partner. Other elements on the periodic table do not just magically now get a 2 as well. It's only these 7. There are 7 of them. They make a 7 on the table. It's more like an upside down L, but it's kind of like a 7. And they start at element number 7. You do want to make sure you know these and remember them. Let's talk about writing chemical equations. We'll do an example and then you'll try a few. So, everything we learned in the chemical nomenclature chapter and everything else we've covered so far is fair game. Chemistry is connected. So here we're going to use our knowledge of writing chemical formulas to write out a chemical equation. It says solid iron 3 sulfide. Iron is a metal, so this is ionic. Iron 3 means plus 3. Sulfide we can get from the periodic table is -2. We're going to cross our charges, so we get Fe2S3, and it's a solid. Reacts with is a plus sign. Then it says gaseous hydrogen chloride. Hydrogen is +1, chlorine is -1. So it's plus HCl when we cross our charges, and it's a gas. To form is an arrow. Aqueous iron 2 chloride. Again, Fe +2, Cl -1. And then the state of matter is aqueous. And that's a plus sign. Hydrogen sulfide gas. So over here, H is +1, S is -2. When we cross them, we get H2S, and we label it with a G. This is what's called a skeleton equation because it doesn't have the coefficients put in and it's not completely balanced. But it does take your knowledge of nomenclature and apply it, which is something you definitely will need to be able to do for the test on this unit. Okay. Using the example as a guide, please pause the video and try to write the two reactions here in the practice section. Please check your answers. Solid iron, oxygen gas, remember that's one of our 7 diatomic. Form solid iron 2 oxide, Fe +2. Oxygen is -2, and we cross our charges. Aqueous nitric acid provided. Reacts with solid sodium carbonate. Again, crossing our charges. Sodium is +1. Carbonate is a polyatomic, that's -2. And you should get Na2CO3. To form, there's your arrow. Water, plus carbon dioxide, and aqueous sodium nitrate. Again, here sodium is +1, nitrate is -1, so they go together. Okay. You have to be able to properly write the chemical reaction before you can learn how to balance, because if you don't write it properly, you might end up with a reaction that never balances out. Okay. Let's learn about balancing. Now, there are many, many, many different methods to balancing chemical equations. If you do not like the method that gets used here, there are plenty of others. The overall goal is to get you to balance the reaction, okay, and then be able to potentially use it elsewhere. We are going to go through one way to balance. Your textbook goes through it slightly differently, and there are plenty of online videos available if you don't like either method. If you've never balanced an equation before, I find that this visual method is one of the easiest to use. And as you practice this throughout the semester, you'll get better and potentially won't need to even show any work at all. So atoms have to be equal on both sides of the equation, and you can see the steps here. You write out the equation, we count the atoms on each side, we use trial and error and multiplication to make our sides equal. Okay, it's nice to leave H and O for last because they tend to be in multiple substances, and I often like to start with my polyatomics. Things you never want to do is change a subscript or add a coefficient in the middle of a chemical formula. So the number you multiply by becomes the coefficient. In our next video, we will do some practice problems on balancing.